Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Essentials for the Design of a GB Ethernet Front End. Our speaker is Heinz Zenkner. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. But nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you can find the chat function in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are about 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer all of your questions promptly. At the end of the presentation, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will also receive the link to the presentation in the next few days, and the recording will be available at our website shortly. But now I will hand over to our speaker, Heinz, and I wish you an exciting presentation.
Yeah, good morning, everybody. I'm happy that everybody can join and the technique works so far. And I go very quick through the agenda that we can go to the, let's say, more important topics within the next couple of minutes. First of all, I will give you, let's say, a short overview of a gigabit Ethernet front-end design. And the next topic will be the functional diagram of a typical design. And then we will go more into the detail of the hardware design to show you a little bit more into the, let's say, technical details than in the schematic. And for one important issue is the necessary key parameters of the components. And yeah, but the next point is the facts about the signal integrity, which has also a strong relation to the component parameters. And then last but not least is the layout considerations, what we have to talk about. The layout together with the signal integrity and the components, let's say, is a key factor for the performance of the whole interface. And then I can show you some EMC results being performed by my colleague in the EMC lab. And yeah, then we come to the point of the questions and answers. So what is it about the gigabit Ethernet design? The gigabit Ethernet design has to be created according to a standard which is quite old. Has been established in the 1999, so quite a couple of years already, and it's still valid. This means we have to follow specific parameters which are defined there. The next point, which is defined there, is the gigabit Ethernet works with 4 wire pairs, so 4 symmetric data transmission channels with a bandwidth of 62.5 megahertz per channel. This means in the end it is a symmetrical RF or high frequency signal transmission which has to be considered. The special features of that gigabit Ethernet protocol, they make it a challenge. Why? Because the Phy itself has a so-called auto negotiation, which means there is a connection configuration protocol, which also in a second layer then takes care about, let's say, the robustness of the connection. So there is something like a control of the transmission density, the run length limitation of the data strings, the DC compensation that the transformers don't go too much into saturation. We will talk about this very soon. And there is a quite high sophisticated bit error correction inside, which altogether means we have a very, very stable and robust connection. But design errors, usually, they don't result in a, let's say, a communication breakdown, but result in a reduced data rate, which is then corrected exactly by this, let's say, quite high sophisticated software or firmware you have into that Phy. This means reduction in the design or in the setup, how we will see in the next slides then, don't necessarily break up the connection, but they decrease the data communication by just data rate degradation. So the signal, also the signal voltage is a 750 millivolts differential at 100 ohms, which gives you, in fact, approximately 5.6 milliwatt per channel, so a quite small signal, meaning the signal to noise ratio, if it is somewhere coupled in via the cables, is not too large. So let's go to the next slide. Which cable types should be used here? You know, there's a wide range of cable types nowadays coming from the history, and there are some cables which shouldn't be used here. And there are like the Cat5 cable, the Cat6 cable, and the categories 8 to 8.1, 8.2, they also don't need to be used. But there is a bunch of cable category 6A, 7, and 7A, which are, let's say, best if you want to use them in gigabit Ethernet design, because they are most suitable and there's a quite reasonable, let's say, quality to price relation. But there's also something difficult if you consider this, because you can't use any length of this cables. Depending on the quality, you know, you have an attenuation, and we have, as we will see, something like a differential to common mode conversion also inside that cable, so that you again have the, let's say, data speed reduction. And when cascading the hubs, you shouldn't use any number of hubs. I have seen really crazy configurations already. And also the network structure, how you cascade them, should be taken into account, because there are errors which appear once in a while. The whole thing breaks down and nobody knows why. So the quality of the cables, and last but not least, the hardware performance of the interfaces of the hardware itself, they decide then eventually if the whole thing works or not. Today we will talk about the hardware performance of the interface, which is, I think, the most crucial point, because there you can make many things wrong, which are very difficult then to find out where the reason is. So if you look closer at it, this is the functional principle here. We have something like, which is called a full duplex transmission. This is a simultaneous transmission of transmit and receiving the data. So all 4 channels work, let's say, at the same time in parallel, and you have transmit channels and you have receiving channels. They are twisted pairs, and there the problem starts. If we look back what I have just mentioned a couple of minutes or even seconds before, we have a different kind of cables, which I have recommended to you. And the unshielded twisted pair cables, they have an impedance of 100 ohms. And the shielded twisted pair cables have 150 ohms. They are defined in the IEEE standard. And you see, the category 5E, 6 and 6A cables, which the 6 and 6A cables, which can be actually used for the gigabit transmission, are available in a shielded and unshielded type. So meaning, depending in which shop you go or what you buy, you can have on the one or the other impedance, 100 ohms or 150 ohms impedance. And the 7 and 7A are always shielded, which means shielded is 150 ohms. So there will be an impedance problem already because of the configuration of the, what I mentioned, 23-year-old definition of the standard already. And the next thing which we have to consider then is the IEEE standard requires a galvanic isolation. Here by means of a transformer, which is here in the middle of my figure here. Here you see the transformer, which normally protects the equipment between the long cables from damage by high voltage, because long cable can normally, let's say, it collect disturbances, what reason soever, can be capacitive, can be inductive, can be many, there can be many reasons, or galvanic potentials between the two, let's say, spots between the hub and the phi. And then if there is a galvanic isolation, this separates then from the phi and from your, let's say, hub. And this prevents also voltage offsets caused, as I mentioned already, by potential differences between the devices, especially if there are long distances between. So the next issue is the transformer here normally has let's say the whole thing has an impedance between primary and secondary here of 100 ohm differential, which means if we have a center tap here, 50 ohms between the center tap to the one part of the signal and 50 ohms to the other part of the signal. It is symmetrical, so meaning 50 ohms to the ground and 100 ohms differential. There is something which primary and secondary of the transformer is connected to the ground. This is at the one side, let's say towards the cable, a thing which is called Bob Smith termination. We will come closer to this point. And the second part, the secondary part, which goes to the phi, it is here the center tap is connected with capacitors to the ground. You see already here there are different grounds. I will explain you later why we have that different grounds. And one issue is, which if you look closer into it, the reason why we have the capacitors is that we have, let's say, DC blocking on the secondary side, meaning towards the phi, and also towards the cable, which, as you can see here, blocks the DC voltages, but the AC voltages can be then drained to the center here, to the ground, because of the capacitance here. So, as mentioned before, the Bob Smith termination, as it is called in the literature, means that each of the channels, is mentioned 4 of them here, the center tap is connected via a 75 ohm resistor here, and then they are here connected together and then going via a capacitor to the, let's call it, shield ground on the left-hand side. This should reduce interference caused by common mode currents, because we have here something which is a kind of, let's say, symmetrization by the center tap here. And this reduces, for sure, vice versa, also, let's say, interference which is radiated from outside or induced by inductive disturbances into the cable, which then drains that noise here to the ground if it is in common mode. But Bob Smith, many years ago, who invented that kind of, let's say, impedance matching here, referred the whole thing to 150 ohms per wire pair. And if we use another kind of cable, then we actually cannot match here the impedance exactly, yeah, because we have different kind of cables. But at least we can, let's say, drain and reduce the common mode disturbances here. So we cannot correct the impedance, but we can reduce the noise according, let's call it, we can improve the EMC. This is the main reason here why we can use it. We improve the EMC behavior towards immunity, towards emission, but we cannot correct any impedance mismatching caused by any kind of cable. There's a certain reason behind, because if you have, the Ethernet cables, they are twisted. These are twisted pairs, and depending on how they are twisted and how, let's say, precisely they are twisted, depending how they yeah, are close to each other, they create something which is an imbalance to each other, and this eventually causes then radiation and also mismatching towards the transformer and the impedance matching to the Bob's mistermination here. So there will be, depending on the quality, on the impedance stability over the length, there will be a mismatch, which is very difficult then to reduce with that kind of circuit design here. Yeah, the next slide shows you the reference design we have set up to make measurements and to give you some ideas how such an interface could look. On the one hand, let's say we have a USB 3.1 connection to a Windows application, to a notebook. And at the other side, we have that Ethernet port and Ethernet interface connection here, which we talk about today. The whole thing works with micro, with a controller from Microchip Technology, which is called LAN 7800, which is the bridge between the USB 3.1 and the Ethernet here. And additionally, we have written a firmware into this whole chip here, where we can measure the data rate and the bit error rate for immunity testing and also for emission testing, that we see how is the performance with different cables, with different EMC measures I will introduce you to soon. And the whole thing is then powered up by the USB-C port, where it gets 5-volt power. This is the schematic here, which shows you the details, which are explained further on the next pages here, but this gives you an overview here. So the Ethernet port here on the right-hand side with the 50 ohm or 100 ohm differential pairs, which go to the transformer. First in the transformer to the common mode choke, then to the transformer itself. On the primary side, we have the Bob Smith termination. On the secondary side, we have here again the center tap RF connection to the ground, and some more circuits I will show you in the detail on the next slides. So the Ethernet transformer itself, we have here an Ethernet transformer which is called LANAQ. It is a machine-produced Ethernet transformer with a very, let's say, high and high and stable quality over the whole, let's say, period of production. And it has, according to the IEEE standard, a galvanic isolation which has to withstand a test voltage of 1500 volts RMS within 1 minute. It has, like mentioned, the integrated common mode chokes here, which needs a high symmetry to reduce the emission and to, let's say, enhance or strengthen the immunity. And and has left and right or primary and secondary side the middle tap, which needs to be then connected to have it as, again, as for the symmetric for the symmetric impedance matching. So on the next slide, it shows you a little bit more of the schematic. Where is the background? The Bob Smith termination here with the 75 ohm resistors has been here connected via two capacitors to the shield ground. The shield ground is the ground which is, let's say, call it an easy way. If you have a metal housing, it is the connection of your metal housing, not the connection of the, let's say, controller ground. This has been separated here, like I will show you on the next slide. So this ground sign here is the, let's call it shield ground, which is mentioned also here. This is the ground of the shielding of the connector here. Yeah, shown here B1 and B2, the grounding of the connector here. Then okay, these two resistors here are just for the LED power supply here, but again filtered with a capacitor here to the same ground. And then the Bob Smith termination again connected with two capacitors again to the shield ground. Why do we have two here? Very simple, because I have put one on the left-hand side, or here we are on the left-hand side of the Ethernet connector, and on the right-hand side one underneath here. So this is the reason to have it symmetric and to reduce the inductance of the PCB of the connection. This is why I have splitted it to two values. So then we have something which is called, let's call it grounding capacitors, which connect here the PCB ground together with the shield ground, and they can be assembled here alternatively. The reason for this is we have done in our EMC lab different, let's say, investigations, different setups, and to see whether it is good to connect them or not, whether it is good to have a direct connection to a whole surface here, not to having separated the digital ground from the shield ground and connected together. And it is like we have supposed before already, in case of a metal enclosure, you should not assemble this capacitors having a direct connection here of that Ethernet and the port C connector here, USB port C connector directly to the housing, and separate the digital ground. You can connect the digital ground directly to the housing, but not on the PCB here. Then because then you have a much higher immunity against, let's say, transients which are incoupled here from the cable to the port, or from the other side, depending on how long the USB cable is. You can separate, let's say, transients which are coupled into that cable. In case of a plastic enclosure, it makes sense to connect this capacitors here having a direct connection with the cable to the digital ground, because then otherwise you would have a floating digital ground here, which would not be in stable setup for a sufficient immunity. Yeah, the next point here is a little bit more depending on which kind of Phy you use here. You see here there are capacitors which tap here, the center taps to the ground here. The reason is if you have a Phy which has, let's say, a DC offset here on the different channels, and you connect them all together, and that Phy works in a so-called standard voltage mode, you may have a DC offset from the one to the other channel, which is then shortened. So if you separate them by this capacitors here, then you have a DC separation here, and you do not short the DC offsets of the channels of the Phy. So depending on the Phy you have, it is normally described in the specification of the controller you use. In case the controller works as a current mode line driver, then you may need to populate here or assemble the 0 ohm resistors and put it here to the voltage supply here of the Phy. Then the whole thing works in a current mode, and seems like that we don't have then this deviation of the DC voltage or DC current offset of the channels. So there you eventually have to look into the specification of the dedicated controller or Phy you use here. Then we have some TVS diodes. Why do we have them here? This is to protect the Ethernet Phy here from transients. If you look at the schematic, let's go back a little bit to the overall schematic here. We have here the cable connected. And all, let's call it transient voltages, transient currents, which are normally, let's say, induced or which are impacted on the cable due to bursts, surges, or RF voltages regarding to EMC immunity, they are converted here in the transformer into common mode, meaning on the secondary side here, you will have common mode disturbances on all channels. So it is necessary to implement here on each channel symmetric overvoltage transient suppression that you can reduce against the ground, not the ground of the housing, but the ground of the controller. You want to protect the controller here. We are on the secondary side of the transformer, meaning the parts, the signal parts, which go to the controller against the ground of the controller, which is the reference ground of these wires here. You have to protect against transient voltages. If you connect this to the primary side of the housing, you're lost. It won't work. Even worse, any disturbances coming from the cable will be here offsetted and have an offset between the digital ground and the ground of your controller. So because this would then be the ground which I mentioned before, this one here. So the TVS diodes, they need a very, very tight, low inductive direct ground, low impedance connection to the reference of the Phy. So the next slide shows you a little bit more details to the TVS diode arrays, because there is sometimes a misunderstanding. The most important point in gigabit Ethernet design is the very, very low parasitic capacitance you need on the lines. Otherwise, the whole gigabit Ethernet, let's say, signal will be impacted. So you see here we have an C cross, like it is called here, of 0.08 picofarad. Where is it here? You see it's here. C cross maximum 0.08 picofarad. This is eventually the capacitance which impacts your signal, not that one. Channel input capacitance. This is to the ground where we want to filter to or to clamp to. The C cross capacitance is the important, which impacts your signal. If too big, if too large, the signal will be attenuated, will be damped. If you don't have a sufficient ground here directly to your Ethernet controller, if there is, for example, a long trace to long distance, you can imagine with this low capacitance, any nanohenry you have here will cause ringing, will cause impedances, which then make it almost impossible to clamp the, let's say, fast transients sufficiently to have sufficient protection for the controller. So also what has to be mentioned, the PCB solder points, like mentioned in my presentation, the wires, the capacitance between the components also must be considered. There is not only the capacitance of your transient voltage suppressors themselves, there are all the stray capacitances around the component, which add up to the capacitance having then an impact on your signal. So this has to be considered in the layout. I will show you on the next slide soon. In case you have another transceiver or another phi that I used here, there are some phis which also need an pull-up resistor having the 50 ohm impedance matching directly on the phi. This I have mentioned here just, let's say, for your information, because I have seen some, let's say, not so good circuit designs here. For example, this 50 ohm resistors, they need to be connected to the VCC, to the 3 volt, the pull-up resistor, right? And if you forget to block it with capacitors towards the ground here, then you have an impedance, and again the 50 ohm resistor, the whole thing won't be matched. So you must here have a very low inductive connection to the capacitors to directly connect these capacitors to the reference ground of the balanced signal here. You know, we have 100 ohm balanced, 50 ohm from each line to the ground. So we need to have here the 50 ohms connected to the reference ground here of the phi. Otherwise, the whole thing doesn't work. This is just to mention it here. And this means if we talk about matching, that must have a reason. The reason is the very short rise time of the signals, the quite high data rate we have here. So meaning normally a signal with a very short rise time, there is a definition in it in high frequency design. We say if the switching transition, meaning if the signal goes from 0 to 1 or from 1 to 0 is completed, if the switching act is completed before the signal has traveled from the source to the load, we have a, let's call it, high frequency signal where the rise time has to be considered. In any case, if there is a mismatch, if there is a deviation from the standard impedance, matching impedance, here in this case the 100 ohms you should have, you will have mismatch. And in the case of mismatch, if the signal hasn't reached the load before the switching transition happens, it will be reflected back to the source. So like mentioned here, the signal is reflected back to the source, and then this means it will mix up with the other signal, which is still on the way. So the old signal and the new signal may be mixed up, and this for sure you can imagine causes then in the best case only some transmission problems. In the worst case, it doesn't work at all. So normally you see it, there's not a black-white transition. If it is on the, let's say, on the border to working and non-working, you will have interference emission. There will be a high emission of the signal because it is reflected, it is radiated. You will have functional impact, which means, like I mentioned before, you will have a decrease of the data transmission. The transmission rate will drop, but it won't break up at all. If it breaks up at all, you should have big impact in the whole layout design. So we have to consider impedance matching and propagation time. And what does it mean? There is according to reflection, there's a rule of thumb. If the trace, the wave from the phi, let's say to the port, is longer than 1/3 of the rise time of the signal, reflections may occur. Reflections may occur in case of mismatch. And as you know, I have mentioned to you, depending on which cables you use and how the layout is done and how symmetric the transformers are and so on and so on, you don't have the 100% matching. So there will be some mismatch. And let's look to an example. What can you do in your layout design, at least to have it there? matched and they have there everything, let's say, how it should be. This means if this example, if the signal rise time is 1 nanosecond and you use FR4 material like it is done in, let's say, 99% of all cases, we have a propagation speed for FR4, which you can calculate, C, the wavelength, the speed of wave divided by square root of epsilon r, the dielectric permittivity. We have 15 centimeter per nanosecond. And as we know, we talk about 1 nanosecond here, then it's 1/3. If the material, meaning the critical length here, if the trace is longer than 5 centimeters, we have to deal with reflections because there the propagation time is longer than the rise time. And another important issue, in case of you have buses like the Ethernet, where you have, or HDMI, for example, where you have symmetrical buses running in parallel, there is a permissible offset between those channels. They're also defined in the IEEE standard or also in your specification of the controller. And let's take one example. If you have 0.1 nanosecond, we have to deal then with about again the 14 0.6 centimeter, or like mentioned here, 14.6 exactly centimeter per nanosecond. And if we have a maximum deviation according to the standard of 0.1 nanosecond, this means if you have a skew, a length deviation between the channels of more than 14 millimeters, which is quite a lot already, you may have impact of the, let's say, whole functionality then. But you see 14 millimeter, which is 1.5 centimeter, is a lot. So if the traces are not too long, it should work. Here, I just want to give you a short overview how to do this symmetric traces here. These are again the 4 channels of our gigabit Ethernet transmission from the Phy to the transformer, from the transformer to the connector here. And the blocking capacitors of the Phy should be very close connected, or let's say placed close to the VCC pins. Then the inductances of that, let's say, traces from the capacitors to the controller should be lower than 1.52 nanohenry. That's the rule of thumb, meaning 3 millimeters, maximum 4 millimeters, maximum not more than this away. And this is already the problem because the Phy is a high integrated circuit, so you have to place them underneath, which means 6 layers will be the minimum what you need here. 4 layers for the, let's say, signal integrity, but 6 layers should be better to place all the capacitors like needed. Then the distance here between an Ethernet couple here and other traces should be more than 3S, which is here defined. You see 1S is 0.125 millimeters here, so you can calculate how the distance should be between, let's say, TTL, CMOS, other signal traces here and the pair here. Then between ground and the pairs should be larger or more than 2S here. And the distance also between the pairs themselves should be 2S. And the distance between one and the other pair here, within the pair, between one and the other signal, the symmetric pair here, should be 1S. But sure, this depends on what kind of dielectric constant you have, and depends not for sure also on the layer stacking you have. So normally we start, I'll show you on the next slides then, we start with putting them as close together as possible and then adjust the width regarding that you have the 100 ohm impedances, which are then according to the standard again. So how does it look in detail? You see here the transformer. There we have the TVS diodes, very, very, very close here to the Phy. Here the Phy starts already, connected directly to the ground, to the digital ground. You remember the ground where the controller has the reference to the transformer itself here, and directly here with the symmetric pairs to the receptacle to the Ethernet port. The Bob Smith termination underneath, so we have a double side assembled PCB here. On the one side, the transformer, at the other side, here the termination components. Also here at the other side, we have the TVS diodes. If you want to assemble everything on one side, you need long traces. It will be difficult. You can't place the Bob Smith termination directly to the pins of the transformer. So any kind of compromise you make will definitely impact the performance of your design. You can try it. You can make a large list of excuses, but it won't work. So the next here is, let's say, the next slide here shows again the TVS diodes, the Bob Smith termination. Yes, again, that's the bottom side of the PCB. Here you see the TVS diodes. Here again in the 3D view here, here the bottom side with all the assembled components here, and here the top side. Looking to all the four layers here, this is a 4-layer board. Yeah, we have the separation, which is the most important here. The digital ground, which is called ground here, the yellow one, the shield ground, the blue one here. You see the strict separation. You should not go over the plates here. There are, you see, through all the layers are really separated from each other. So no overlay between them. Yeah, that you really have strict separation. Yeah, and you need you see here a very tight signal trace coupling between the traces themselves here, and sufficient distance to the ground here, to the shield ground, that you don't have any coupling. This is thing which is, especially at the shield ground side, essential for proper functionality. Then you see we have here wires, all 4 millimeters, each and every 4 millimeters here, to couple all the layers stacks together here, all the planes, yeah, that we really have a tight ground, really have a sufficient shielded ground here underneath. And the TVS diodes, as mentioned already, here they are here in the bottom view here, are connected directly with 2 wires through all digital ground layers here. And on the next slide, you see here the stacking, the layer stacking. The top layer ground here, you have some the thickness. It's standard setup, and the dielectric constant here. You know that the top solder has a little bit a lower dielectric constant, which has to be considered. Then, if you have the top overlay on it, the solder mask, it will change the behavior of the impedance. So this has to be considered then. And yeah, then I have a summary, which is more or less not something I want to go through here step by step, because the time is over, as I know. And it is more, let's say, a summary of all what I have mentioned here in that some couple of minutes, which normally should have more time, but at least here you have the summary. You can go through it once you have the presentation here. And yeah, I think now we go to the questions and answers. No, I forgot one. Sorry. This is the EMC result. You see, if you look at the radiated emission here, the vertical and the horizontal, you see that we have sufficient distance. That's under full speed condition. The immunity here has been measured against the industrial levels and can be passed here without metal housing, which means we have a high immunity. Yeah, high immunity against all the bursts and surge and radiated immunity requirements. And we have, yes, you can see more than 15 to 20 dB distance in the radiated emission. Okay, this was in ultrasonic speed, the requests, the necessary requirements for the gigabit Ethernet design. Let's go to the answers and questions.
Thanks a lot, Heinz. Yes, let's take a look. What questions will come in? Maybe one first question, Heinz. How do you rate quality of the connection during EMC immunity test?
Yeah, we have created on the lab view. We have created an a software which can see we can measure the data rate and the data error rate, the data speed and the error rate. So during the immunity tests, we have a Windows application which on the one side goes to a computer which is decoupled in a shielded box or outside our immunity chamber in the EMC lab. And then we have a tight connection on the, let's call it the secondary side, the computer side, of the shield to the cabin, if in case it is a shielded cable. And at the other side, we have our test Ethernet connection. And then we measure the data rate and we start immunity test. We increase the levels. For example, for the bursts, we start at 500 volts, go to 1 kV, go to 1500, and then we see, and this is how it affects. And this was what I mentioned in the beginning. There is one big problem. You won't lose the data connection at all because of that high sophisticated, let's say, data correction, data error rate correction, but it will, the data rate will go down. This you can see. And then you can see where it starts having impact on the immunity. And then you can change whatever you like in the hardware or changing the cables, and then you see directly the impact. But actually, you need this software. There are some hardware, let's say, data readers on the market available. I know, but they are quite expensive. And if you just need to develop one Ethernet port for one, let's say, application for one product, yeah, it's challenging to give a lot of money for this. So we have eventually developed the software for that reference design here.
Okay, thanks a lot, Heinz, for the explanation. Maybe another question. Do shielded CAT5E and CAT7 cables have different impedances? Do you have an answer
If
to
they are both
this?
shielded, they should have, yes, if they are both shielded, they should have the same impedance. But they the CAT7 is, as I know, is separately shielded, is they are separated from each other, the pairs, and in CAT5 not. Yeah? This means the coupling between the channels themselves are a CAT7 are more separated. There is not such a big impact from the one pair to the other pair. They are separated from each other. So what means that gives you a higher accuracy according to the matching to the impedance stability. So the impedance is more accurate.
Great. Thanks a lot, Heinz. I would say because of the time, if there are any questions left, we will answer them via email afterwards. But for now, thank you very much, Heinz, for your presentation, and thanks a lot to all of you for your attention. The next presentation topic is secondary side compensation for isolated power supplies, and will start at 1 p.m. from our partner Microchip Technology, and the speaker is Carlo Lombardi. So see you there, and thanks for your attention. Bye.